All right, everybody, welcome back. This is lecture 2 entitled Arduino Serial Communication. So in this lecture, we're going to go into a bit of detail of memory management and different variable types. This is really important because when we're acquiring data from, for example, sensor nodes with Arduino, we need to be conscious about how that data is collected, how it's communicated, and how it's stored. And that is often done over serial communication. So first, I need to warn you, things are now going to get a little bit technical. It is, without a doubt, the most technical that these lectures get in terms of memory management. But don't worry, the concepts aren't too hard. It is really just to warn you about some dead ends that you might get to with your projects when it comes to collecting data and doing serial communication. So let's get started so you can understand some of these important points. So first, let's talk about how data is stored in memory. First, I want to introduce the notion of a bit. A bit is essentially the atomic unit of data. And a bit is binary. It's 0 or 1. This is the atomic unit of data. Now, the next largest unit of data, think about it like a molecule, would be a byte. And a byte is comprised of 8 bits. Right? So we have 8 digits where each digit represents 0 and 1. So it turns out if you converted these 8 bits into decimal form, you could basically enumerate out 256 items. So in decimal, a byte would be each value in a byte could be represented by numbers in the decimal system from 0 to 255. So 2 to the 8th or 256 values. It can also be represented in hexadecimal. So what is hexadecimal? This is base 16. And the way it's often denoted is by 0x and then these hexadecimal digits. Okay? So the 0x is really just a signal that says, hey, I'm in hexadecimal. And then each digit is a value that goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So that's 10 numerical digits, and then we'll use the characters A, B, C, D, E, F to denote the next 6. So it's base 16. This is hexadecimal, and the other important point is it's often denoted by 0x. The 0x doesn't mean anything besides, hey, we're talking in hexadecimal now. Okay, so when we declare variables, like an integer, a character, or a string, then a certain amount of memory is reserved for that variable. So for example, if we declare an integer variable, like LED in the last lecture, then it turns out Arduino will reserve 2 bytes of data to store the values for that variable. So for example, in hexadecimal, that would be represented by all the hexadecimal values between 0000 all the way up to FFFF. Okay? So those are 2 bytes. All right. So that was the example for integers. Let's talk about all the different variable types in Arduino, at least the ones for numbers. So in Arduino, an integer variable type can store any integer between negative 32,768 all the way to positive 32,767. Okay? We can also store unsigned ints. So these are integers for which we are not interested in storing the sign of it. So for example, we always know that we're interested in positive numbers. If you're in that case, then you can store values from 0 to 65,535. So you've basically doubled the values that you can store. Now, if you're interested in storing numerical values that are larger than that, you can define what's known as a long integer. So that's a number that's between roughly minus 2 million to positive 2 million. And similarly, there's an unsigned long integer, which is an integer between 0 and about 4.3 million, as shown here on the slide. So as you can imagine that when you define an integer or an unsigned integer, those are only 2 bytes of data, as we discussed on the previous slide. For long integers, those are more bytes of data, so they'll take up more space in your Arduino if you store those. What takes even more space is doubles or floats. So you can see here that's a decimal value between minus 3.4 times 10 to the 38 to plus 3.4 times 10 to the 38. So you can see that has 6 to 7 digits of precision, and doubles and floats consume a lot of memory. Why do we care? You certainly don't care on your laptop. You have plenty of memory for this purpose. However, your Arduino has a very limited amount of memory, so you will quickly run into these issues. These are the type of practical concerns that you come up with when you're working with Internet of Things types of devices. For more information, check out this Arduino reference page link on the right-hand side of the page. Okay, so let's explore the role of precision and these different data types by doing some Arduino arithmetic. So let's consider integers. If we do arithmetic with integers, then we will get integers. So for example, let's consider the following, where we really need to pay attention to order of operations. So suppose that we define this integer variable type, we'll call it r, and we have not initialized it. In the first line, I'm going to write r equals 9 divided by 10 times 100. If I do that, then what will be saved or assigned to r is 0. Why? Think about order of operations. First, it'll do 9 divided by 10. Now, we understand that as having a value of 0.9. However, because integer arithmetic generates integers, it'll round to the nearest integer towards 0. Okay, so if it's positive numbers, it'll round down. If it's negative numbers, it'll round up. It rounds towards 0 to integers. So 9 divided by 10 will produce 0. 0 times 100 is 0. That's why r equals 0 in the first line. Conversely, if we do 9 times 100 divided by 10, what's assigned to r is 90, because 9 times 100 is 900, divided by 10 is 90, so we get the result of 90, which may be what we intended in the first place. The third example here is also interesting. It's kind of like the first one. If we use parentheses to dictate order of operations, 9 times 100 will give us 900, but if we put in parentheses 1 divided by 10, that'll give us the result of 0. It'll round towards 0 to the nearest integer, so it'll look like 900 times 0, which equals 0. So it'll get assigned to r is 0. Okay, we also need to be conscious of this issue of integer overflow. So if we define an integer variable, then the maximum value that can be stored there is 32,768. If we add 1 to that, then what gets assigned to r is minus 32,768. So what is it doing? It's basically going to the other end of the possible values for integers. It's you've basically gone across the globe, so you've reset to the other end of the possible values for integers of type r. Okay, why would this ever come up? You'd be amazed how often this comes up. Sometimes you're incrementing something in a wireless sensor node that is collecting data for months at a time, So you will sometimes run into these issues. Okay, so how do we handle this issue of doing arithmetic the way we want while still using integers which have this nice tight data space that they require, just 2 bytes? So one way to do that is with something called typecasting. So suppose we define the variable r, okay, and I want to do the calculation of 9 divided by 10 times 100 and save the result as an integer. Typecasting, basically what it does is it says, if I use this syntax where I put float in parentheses, what it'll do is it'll temporarily create some data types that are of type float to enable the calculation on the right hand side of the equal sign, and then it'll take the result and cast it into an integer. So then 9 divided by 10 will be computed as float variables. You'll get 0.9 times 100 produces 90. And then it'll convert that back to integer, which will be assigned to the variable r. A similar concept is type conversion. So here, what I'm going to do is convert 9 into a float. So that's what float parentheses 9 means. So now the Arduino conceptualizes 9 as a floating variable, and then all the arithmetic that it does on it will be a float type. Okay, so here you'll get the same result of 90. The integer 90 will be assigned to r, but what it's doing is it's basically saying, Arduino, treat 9 not like an integer, but like a float, so then it can do floating point arithmetic on that variable. Okay, now that said, you generally want to avoid float arithmetic. It may seem very comfortable to you. It's very comfortable to me as a mathematician. I want things to be precise and exact. That is why we have mathematics. However, sometimes it is not exact because of rounding errors, and it turns out it's much slower on the Arduino compared to integer arithmetic or integer mathematics. The reason for this is because it takes up a lot more memory when we cast things as float. So while that may seem trivial and perhaps things that you might be concerned about when computers were first being developed, keep in mind we're talking about a $30 computer, perhaps even cheaper, if you're doing a really small, cheap wireless sensor node. So we typically have to manage these types of issues. Okay, so, but there's tricks to handle this. It's not that bad of a thing to deal with. So you could change units. So for example, our sensor readings will often be measured in volts. And our Arduino can measure between 0 and 5 volts. So rather than working with units of volts, if you work with units of millivolts, now you've changed the values 3 orders of magnitude, and it's easier to work with integers than floats. So that's a common trick, really best practice, and something that folks use all the time with sensors. Okay, let's talk about other Arduino variable types besides numeric ones. There's void. So void is really just null, so empty space. Boolean is true or false. And then we have characters. So how are characters saved? They are saved with the ASCII code chart. So I have some examples in this table here. How is the character exclamation point saved? So it turns out that we have these ASCII code charts, which are basically language translation tables. So for each character, we have a corresponding decimal value and a corresponding hexadecimal value. So each character gets assigned to it 1 byte in hexadecimal. So for example, it turns out that assigned to the character exclamation point, we have the hexadecimal value 21. Okay? And similarly for all the characters that you might find. To do this translation, you can click this, I think it's a link, yeah, for the ASCII code chart. So this is pretty cool. Goes to the Arduino webpage, and you can see the decimal values and the characters here. Okay, so let's explore this. Let's define the variable type R. We won't initialize it. We'll do that on the next lines. So suppose I have the character A, which is denoted in single quotes, and I would like to save the integer value corresponding to A and assign that to R. So if I look at my ASCII table, you'll see that character A corresponds to a decimal value of 97, which is an integer value, and that is what gets assigned to R. Now, this one's interesting and a little bit tricky. Let's consider the character 2. The character 2. Not the numerical value, the character. Okay? It turns out that the character 2 corresponds to a decimal value of 50. So 50 will get assigned to R. Alright, let's consider a slightly different example. Suppose I define a different type of variable. Its name will be C for a character. It's going to be of type character, and I'm going to initialize it with the value, the character, A. Okay? Now, if I do C++, that basically means I'm going to increment the value that's in this variable C, which it turns out to be A, the character A, and I'm going to increment it by 1. What that basically means is I'm going to go to my ASCII table, and I'm just going to go down one row to whatever the next character is. In this case, it's B. All right? And here, it turns out that if I said C equals 99, because the variable C is of type character, it understands that what I want is the character corresponding to a decimal value of 99. So what actually gets assigned to character C is the character C. Right? We're overloading C here, but point is that it understands that if I say C equals 99, it means assign to the variable the character corresponding to the decimal value of 99, in this case C. So if I said C equals 38, then what would get assigned to C is ampersand. Okay, here's an ASCII code chart. I just want to highlight a few special characters in this ASCII table. Backspace, horizontal tab, new line, and carriage return. Why are those important? Well, when we do communication with the Arduino, sometimes we want to go to a new line, so we'll need a carriage return, or we just want to define an empty line, or we want to give some space with a horizontal tab. It turns out that there's ASCII characters corresponding to that. So pay attention to those. Those will be very useful, and even in Lab 1 Part 2. Okay. Next, I want to do an example, demonstration with our Arduino and the IDE to really demonstrate how this works. So here's what's going to happen. We are going to essentially create a serial communication channel with Arduino. So it'll be between our Arduino and the laptop. And then what we're going to do is send characters to the Arduino from our laptop. The Arduino is going to execute some code, which is shown here on the slide. And then the Arduino is going to spit back something in the serial monitor based off what we give it. Okay? So let me jump into the IDE to explain how this works. All right. So what I have here is a sketch called Serial Echo Exercise 2. And let's walk through what it does step by step. So first, we're going to define a variable called incoming byte. It's going to be of type integer, and I'm going to pre-allocate it to have the value 0. What is the role of incoming byte? The role of incoming byte is the Arduino is going to listen to the serial communication channel. It's going to wait to see if there's any data being sent from our laptop to the Arduino. It's going to listen, and whenever there's any data available on that communication channel, it's going to save the byte into this variable called incoming byte. Okay, you'll see how that works in just a second. So in the setup function, we're going to initialize the serial communication. So serial.begin 9600 for 9600 bits per second. And now most of the action happens in this loop function. So first, I'm going to check if incoming content has been received by the serial port. So here's what's happening. It's going to continuously loop through all of the commands inside the loop function. And if I'm not typing any information into the serial monitor, then nothing is being received from the Arduino. So what it's doing is it's just waiting and checking to see if any content is being sent from the laptop to the Arduino. Now, if content is received, it'll be it will be detected by the command, by the function here that is in the argument of the if statement. So specifically, serial.available looks to see if there's any data available in the serial communication channel. And if the length of that data is greater than 0, that is, anything exists, then it'll execute the code inside the curly braces here. So what it'll do is if any data is sitting in that communication channel, then it'll read the next incoming byte. So I'm going to use the function serial.read, which will basically look at the next smoke signal, right, that I get in the communication channel, and then it'll assign the data, literally the bytes, into this variable called incoming byte. And this variable, incoming byte, is going to be a byte in hexadecimal representation that corresponds to the character that was sent over the communication channel. So let's use the smoke signal analogy again. What happens is serial.available greater than 0 means you're looking out to the other hill and just waiting for smoke. If you see any sort of smoke, then what you'll do is a serial.read. You will read what type of pattern in that smoke is being sent, and then it corresponds to a character, okay, some sort of character, and that'll be stored in incoming byte. It'll literally be stored as some hexadecimal quantity, but it corresponds to a character via the ASCII chart. Okay, so we've stored that in incoming bytes. Now, what the Arduino is going to do is going to echo back this character. So we're going to use the command serial.write and give it incoming byte. Now, the following is important and is a common mistake in a common obstacle or question in Lab 1. So .write knows that incoming byte is of type, it is a byte that corresponds to a character. So it'll send a byte and that corresponds to the character, and then your laptop, namely the serial monitor, will show the character corresponding to that byte. So basically, the Arduino is just echoing the smoke signals that you're sending it. The next line, or the next command here, is serial.printLine, is going to give a semicolon. And what print line does, as opposed to just print, is it prints this literally this character in single quotes, and then a carriage return that automatically is added when you do a print line. Okay, so that's nice because it'll basically show all the characters. It'll echo the characters on new lines, right? So let me just upload this so you can see how it works. Okay, so it's done uploading. I'm going to open my serial monitor here. Okay. All right, so now the Arduino is sitting and just listening to the smoke signals that I send it. So suppose I send the character A. All right, so what happened here is the Arduino noticed that there was data inside the serial communication channel, did a serial.read, and it saved a byte, which is literally the hexadecimal number corresponding to the character A. So that is now stored in the Arduino as incoming byte, and then it ran serial.write with the argument or the input incoming byte. So it gave the hexadecimal value corresponding to A, and then it wrote that, it sent a smoke signal back corresponding to this byte, and then our laptop interprets it as the character corresponding to that byte. In addition, it appended to that the semicolon, and because it's print ln, it does a carriage return. So if I do B, then it'll show that on a new line. Okay. So to be clear, what's being stored in incoming byte is hexadecimal value 61, which corresponds to the character A. Okay. All right. So just to test our understanding, I'm now going to change this write to print. What does that do? Print is different. Print thinks you want to send literally the values in incoming byte. So let me just upload this and we'll see what happens. Okay. So now I'm going to send the value of A. It says 97. Why is that? So I sent the value of 97. It did a serial.read, and what is stored is the hexadecimal value corresponding to the character A. So if I go back to my table, it corresponded, it saved hexadecimal 61, which also corresponds to decimal value 97. That's literally what's stored in the Arduino variable. Okay, now when I did a serial.print with incoming byte, it does not understand that this corresponds to a character I want to send. It thinks I literally want to send the value 97. So what print does, it'll send the characters 99 and 7, and then it'll append to that set semicolon. Okay? So for example, if I send ampersand, shown here, I'll get 38, which we'll note is the decimal value corresponding to ampersand. Okay, so let me change that back to writes, and then just so you understand the difference between print and print line, I'm going to change this print line to print, and now let's re-upload this sketch. Okay, so if I send A, I get A back. If I send B, I get B back, but note, I did not get a carriage return. It did not put it on a new line. However, luckily, I have these semicolons to annotate the difference. Let me also mention that if, I send an entire word, like, let me send my name Scott, okay, what it does here is, because it's serial communication, it'll send it one character at a time. So when it goes through this read the next incoming byte part, does a serial.read, basically it's queuing up all these characters. So serial.read will look for the next incoming character, it's S for Scott, it'll store the byte, and then it will send that character back to us. It'll echo it back to us with a semicolon. So you can see how it queues up and will echo back one character at a time. Okay. All right. Now let me talk about variables in memory. So as we discussed before, we have different types of variables: Boolean, characters, bytes, integers, unsigned integers, so on and so forth. You can see here how much bytes of memory that they take, and you can also see the min, median, and max hex values. which correspond to the amount of bytes that it takes to store this data. So be conscious in your projects of how you store your data. This is data science at the most fundamental level. Okay, now you may be saying, oh my goodness, this is so deep in the weeds. Why in the world are we doing this? Again, let me emphasize the context. This is super practical. Arduino is an embedded microcontroller, which means it has limited memory, limited computation, and you can reach your resource limits super fast. So memory management is often necessary. Maybe some of you will get away with ignoring all this, and you'll just say, well, when I run into an issue, I'll deal with it when it comes. Okay, fair enough. But at least you're aware that it can be an issue, so you can look out for it. And if it is, then you can come back to this video and figure out how to be a little bit more thoughtful about your variable types, arithmetic, so on and so forth. Okay, let's talk about building a cyber-physical system. This is really now getting towards what your projects will look like, and also what Lab 1 Part 2 is about. So why do we care about learning about bytes? So typically, we're going to have an Arduino, which might be connected to, for example, an XBee radio, which is what you're doing in Part 2 of Lab 1. You are going to do serial communication to communicate information to that radio, which then might wirelessly send information to another radio that is somewhere else, like a base station which is collecting all that data. That radio, through serial communication, will send information to another Arduino, which might be connected to a PC, which is connected to Wi-Fi, which is collecting everything in a server. So all of this will occur with serial communication. We need to have some idea of how this occurs and how these bytes are sent. So this is really the building blocks of a cyber-physical system. Okay, let me take a minute to talk about wireless communication. There are a few types of specifications for wireless communication. I'm going to highlight 3 of the most famous: ZigBee, Bluetooth, and Wi-Fi. So Wi-Fi is what you use to stream videos. Bluetooth is what your phone might use to connect to devices like my Fitbit here. ZigBee is a different type of radio frequency and specification for wireless communication, really typically used in Internet of Things. So what I want to highlight here is basically the order in which these are given also correspond to the data rate. So if you're streaming video like Netflix, you want Wi-Fi. If you're basically collecting one temperature measurement once every 10 minutes, Wi-Fi doesn't make any sense. You do not need that data rate, and if your wireless sensor node is battery powered, you're going to burn up a lot of your battery energy using Wi-Fi when you honestly could get away with ZigBee. So this is like a Goldilocks scenario. You know, do you want the porridge too hot, too cold, or just right? When it comes to Internet of Things, you may find that a ZigBee protocol, which is very, very low power, might serve your needs. You might want to have, 65,000 nodes. So those types of specifications might make sense if you're talking about sensor networks. Okay, there's other things to consider, like range and data rate. So we've already talked about data rate. Wi-Fi, ultra-wideband, 3G, 4G, these are really great for streaming videos. Bluetooth is this intermediate scenario. ZigBee has low data rates, as we've already discussed. They also have various aspects when it comes to range. So things like GSM, 3G, 4G, LTE, those have larger ranges, generally speaking. ZigBee has a limited range, but compared to Bluetooth at least, it typically has a larger range. So it's pretty good for things like building automation, say doing a wireless sensor network in a manufacturing facility that is quite large. Think like the Gigafactory, for example, so on and so forth. Okay, let's take a closer look at XBee. XBee is a product. ZigBee is the wireless communication protocol. Now, XBee is a ZigBee product by a company called Digi. It's just one product that uses ZigBee. It's the ones that we happen to be using in this course. You'll notice that there's actually two series, Series 1 and Series 2, which have different specifications. Generally speaking, Series 2 is has larger range. It has more transmission power, and the other thing about it is, well, it's more expensive, but it also enables for mesh or star configurations as opposed to strictly peer-to-peer or paired communication. Okay, what does that mean? That's really described by these network topologies on the next slide here. So if you have a sensor network, which is really just comprised of a pair of wireless devices, then Series 1 is great for your purpose. You can pair up those devices, and that's essentially what you're doing in Part 2 of Lab 1. However, if you have a more sophisticated, a larger wireless sensor network, they may have a more complex topology. For example, a star topology, or an N to 1, so you have N nodes that might each be in communication with a single central node. This is like a hub. We call this a star topology, or I like to call it N to 1. Alternatively, you may have a cluster tree. So here you have these routers, which are basically serving some end wireless sensor nodes. They aggregate the data, and they will send it to a coordinator, and perhaps this coordinator will then send that data up to the cloud. So the only thing that needs to be connected to the outside world would be the coordinator. Now note, this has a radial structure. There is essentially kind of a hierarchical structure here. At the top of everything is this coordinator, and then you could flow down this tree. Trees and radial structures are often synonymous. In contrast, you may have a mesh structure. So this is a topology which is not radial in nature. There is no clear hierarchy of what's on top and what's on bottom. So here it's a more complicated situation where some nodes might be in communication with some other nodes. And frankly, we often see in wireless sensor networks that we're in a situation where we're either a cluster tree or a mesh. And in those cases, you want Series 2, which is what we have in this class. Okay, the last thing I'll highlight about wireless sensor networks is there's this inverse square law property, meaning assume that you're in an open field. The transmission power of a radio goes down proportional to the radius squared. Okay, so if you have two nodes and you double the distance between them, then the transmission power goes down by a factor of 4. Right? This is very important when you're thinking about where to place your wireless sensor nodes, for example, in a building, or for example, in the Sierra Nevada mountains, if you are building a wireless sensor network to measure snowpack depth, like in Professor Steve Glazer's research. Okay, that's all I'm going to quickly say about wireless sensor networks, just to give you some idea. A great textbook on this that I definitely recommend is by Faludi. It's called Building Wireless Sensor Networks. It's awesome. First and foremost, because it's got these adorable dogs on the cover. You know it's awesome when it's got dogs on the cover. But secondly, it's just really a great resource to build wireless sensor networks. So a number of you may be doing this for your projects. If you really want to get into wireless sensor networks, check out this book. There's a digital copy available through UC Library. You can search online for that. With that, I'm going to close this lecture. There's a few notes following. They're appendix slides. You can refer to them on B courses to help you out with the lab assignment. So thanks a lot, and I'll see you next time.